Welcome to Lecture 17 in our class in Stochastic Process Theory. With Lecture 17, we will start the final chapter of this lecture series, which will be the theory of stochastic integration and stochastic differential equations. The key concept in this is the notion of the stochastic integral. And the first part of today's lecture, or essentially the first part of today's lecture will be a motivation why we would want to have such a concept of a stochastic integral. And the second part of today's lecture will be an explanation of the naive approaches that you could take to the introduction of such a notion and the challenges that lie ahead when you actually want to deal or when you want to apply such a concept to the case of, for instance, Brownian motion. Okay, so let's start with the motivation section, why we would want to have such a notion of a stochastic integral. And the first example is taken from mathematical finance, more particularly the theory of stochastic markets, stochastic stock price markets, where, for instance, we want to do analysis, computations, and evaluations of certain functions which depend on the price dynamics of a randomly moving stock price. So let ST be such a model of a stochastically moving up and down moving stock price. We could think of this as a stochastic process. Of course, for instance, it could be a random walk if we work in discrete time. But we have seen in the context of the central limit theorem and the construction of Brownian motion that if we pass to a continuous time description and do a proper scaling, then Brownian motion itself would be a first not so bad model for the motion of a stock price. So think of ST being the chart that you realize when you observe one motion of a stock price as time evolves. In other words, BT or ST would be the price, for instance, of the Daimler-Benz share on the stock market at time t. And now we place ourselves in the perspective of an investor who at any moment of time owns a certain amount of shares, and let theta t be the number of shares that the investor owns at time t. And at the same time, the investor has a certain cash amount on his bank account, say, and let CT denote this cash amount. So his entire portfolio of wealth, if he has just these two different options to invest, namely into just putting money into his deposit or buying shares, then his portfolio effectively consists of these two quantities, theta t and CT, which represent his total wealth. And so if we introduce the notion pi t, or the quantity pi t, which is the price or the value or the portfolio, the value of the portfolio of this investor at time t, then it is the number of shares he has, that's theta t, times the actual value of that share at that moment t. So that's the contribution of the share, of his share property to his total wealth. And of course he has CT amounts of euro, say, in his bank account. So his total wealth or his total portfolio value at time t is given by this expression. We want to adopt a continuous time perspective, but assume for a moment, which is typically also the case in practice, that the investor can make investment decisions only at a discrete sequence of times, which are separated by a time step of epsilon. So he makes his first decision, if you like, at epsilon equals 0, and then the next decision he may take is at time epsilon. The next moment when he can readjust and reshuffle his portfolio will be at time 2 epsilon, and so forth. And suppose that at each moment of time, when those discrete moments of time appear, he can reorganize his portfolio, but it should be done in such a fashion that it is self-financing. So we want to assume that the investor does not take any money from anywhere else except from his cash account in order to purchase a little more Daimler stock at a certain time point, 2 epsilon, so for instance. So all the transactions that he does at moment of time t should be budget neutral, which means that in any of those time points, the wealth of his portfolio at the time exactly before he makes this readjustment should be the same as the value of the portfolio immediately after he did his readjustment. So we think of a readjustment at an infinitesimal time in the transition from 1 epsilon time interval to the, or in the transition at these transition times, which are multiples of epsilon, when the investor reorganizes his portfolio in a self-financing fashion. And what does this mean? Well, at the end of the kth interval, what's the total wealth of this investor? Well, he had started his, he's at the end of interval k epsilon, the amount of stock that the investor owns is still equal to theta k epsilon, which is the number of shares which he was possessing at the beginning of the corresponding interval. The interval here, which I want to consider, is the interval from k epsilon to k plus 1 epsilon. And I want to consider the investment readjustment that the investor does at this moment of time. At moment of time t equals k plus 1 epsilon. Okay, so what's the total wealth that this investor has at this moment of time before he readjusts its portfolio? So he entered this, or he made a certain investment decision at the beginning of this interval, where he defined, or where he just managed to buy exactly this amount of stock. And then in the meantime, he kept his amount of stock in this whole interval constant, but the stock developed in this time, which means that at the end of this interval, his total wealth, or the component of stock, the stock component of his wealth, is the total amount of stocks that he owned throughout this interval times the actual value of the individual stock at the end of this interval. And of course, he owns this cash amount that he had at the beginning of this interval and which he didn't touch. So this is his total. This number here, which we have here, is the total wealth of the investor at the end of this interval. And now he makes a decision to readjust his portfolio at the transition from this interval to the next. So exactly this point here, in this time point, which I painted blue, the investor readjusts his portfolio, but the requirement of self-financing readjustment says that the total wealth of the portfolio after the readjustment, which then is expressed like this, namely it's the total amount of stock that is owned at the beginning of the next interval times the value at exactly this transition point when the readjustment of the portfolio is being done, times, so that's the one component plus the corresponding cash component. So we want that these two quantities are the same, and these two quantities represent the wealth or the portfolio value of the investor at the end of the interval from k epsilon to k plus 1 epsilon. And this is the wealth, the right-hand side of this equality is the wealth of the investor at the beginning of the subsequent interval. And what we want, and this, these two components, theta k and ck, they are chosen in such a fashion that the total wealth at this transition time is the same, which just means that all the money that is gained or taken or invested for a readjustment of the investment portfolio with regards to the stock is taken from or is fed back into the cash amount. This is what we understand by a self-financing investment strategy. So it's a pair of theta and c values which are updated at each of those discrete moments of time, and we want that these readjustments at each moment of time are cash neutral, so to say, or budget neutral. Okay, and then we can ask ourselves, what's the actual change in portfolio value when we evaluate at two really subsequent intermediate points? So we ask, what's the portfolio value at two subsequent time points? What's the actual change in portfolio value? If we compare, if you like, the portfolio at the end of the next interval, k plus 1 epsilon, with the portfolio value at the prior, at the end of the previous interval, well, by the definition of our by our self-financing strategy, this portfolio value is just the same as if we insert the portfolio value at the infinitesimal moment which was right before. So basically it's the portfolio value at the end of this previous interval, before we did the readjustment of the investment portfolio. And so by what we have just said, we introduce or insert just these numbers. So what's the value of the portfolio at the end of the previous interval? It was the amount of cash or portfolio, the amount of stocks owned at the end of this period times the value of the stock at the end of this period, plus the cash amount that we were having throughout this period. And we subtract the corresponding number at the beginning of this interval, which is basically the same number, except that so the coefficients theta and c are the same, but what has changed, of course, is the value of the stock, which was a different one at the beginning of the corresponding interval. So therefore, almost all terms here in this difference cancel, except for the product of the theta with the difference of the stock value b at the two corresponding endpoints of this interval. And hence, if we ask ourselves what the total change in portfolio value, if we ask for the difference with regards to two time points which are more than one step away, we just have to sum up all the respective differences. This, what we have here, is a discrete, is a finite sum, which involves the values of the investment portfolio in terms of the stock partition of the stock component, multiplied on each of those subintervals with the respective increment of the stock value. And if we write this in a slightly different fashion, namely we write epsilon as the fraction of a certain terminal time t over n, when n then denotes the number of steps, we can equivalently write this as this finite sum, where on the right-hand side we just have rewritten this difference of the b values in terms of the corresponding time points tk plus 1 and tk, when now the time points are enumerated according to this grid with step size epsilon, which we then also write, if you like, in a slightly more intuitive fashion as this a finite sum of theta values times the increment values. And tk, as I just said, is in enumeration of these discrete time points. Okay, and here n in this case would be just the number of trading points, or the number of trading times inside this time interval from 0 to t. So in this way, in this notation, capital N would be the number of trading points if we fix a terminal time capital T. And we see here that we have these numbers, or these sums of these weighted increments of the stock price, where the weighting is according to the number of stocks that we owned in the respective time interval. So that is the situation when we have a discrete finite number of trading points, but for instance in times of high frequency trading and so forth, this discretized, time discretized perspective is probably not completely correct, and we would want to have a possibility to pass to a situation when we have infinitely many trading times or in infinite high density moments of time. So in other words, we want to send this grid parameter n to infinity. And then we see what we have here. This is reminiscent of some sort of a Riemann integral in a way, where we multiply this function theta at time tk with an increment, which is now not an increment with respect to the time parameter, but is an increment with respect to the value of the Brownian motion at these different time points. So we are tempted to write, when we take a limit for n to infinity, by the analogy with the elementary theory of integration, we are tempted to replace this finite sum, if n tends to infinity, by a symbol which would look like this. It would involve some sort of an integral over the theta function when it is integrated against the infinitesimal increments, not of the t function, but of the function which is obtained by evaluating the stock value, the bt, at each moment of time. Okay, so that's an instance, the first instance, where we would want to be able to deal with a symbol like this, which would be an infinite sum, so like a continuum sum of sums, if you like, of a certain function against the infinitesimal increments that we observe if we follow a Brownian motion. For instance, when we integrate this, or when we sum up all these weighted increments of Brownian motion from a certain starting point 0 to a point t. So we would really think that this would be very desirable to obtain, because this would then denote and would describe the total change in value of the portfolio, which is of course a very important quantity, if we follow the investment strategy which is given by theta. So if we fix a priori a certain investment strategy, which is described in terms of the theta function, then this stochastic integral, which is yet to be defined, would describe the total change of value in portfolio, or the total portfolio change, the total change in the portfolio value, if we compare our initial portfolio value with the portfolio value at the terminal time when we want to finish trading. The second motivation why we would want to have the notion of a stochastic integral comes from physics and from dynamical systems, of course, which are abundant in physics and which we want to perturb by random forces, effectively. So suppose we have a certain velocity field and we want to consider the motion of a tracer. So in other words, you consider a swimming pool which has a certain velocity field for the motion of the water, and you just throw in a table tennis ball and want to observe its motion as it flows along with the floating water. If V denotes your velocity field in your container, here the container would be just d-dimensional Euclidean space, then the tracer would be, or the motion of the tracer would be obtained by solving the corresponding dynamical system or ordinary differential equation in d-dimension. X dot velocity equals velocity, surrounding velocity at time position at position x. So that's the picture here. In green, we depicted as arrows the velocity field, and the red curve would be the integral curve or the solution to such an ODE when we have a time constant, for instance, velocity field v. So you could think of that the red curve being the actual trajectory of the table tennis ball, which is thrown into this swimming pool. Okay, now we want to assume that the table tennis ball is in fact so small that it is subject to kind of the same forces as a pollen molecule. So we think that there should be more to it, namely that there's still this Zitterbewegung, this fluctuation behavior in it, and we want to include this into the model in order to obtain a more realistic model, which also involves for thermal fluctuations. So therefore, we are tempted to write that the change of position or the velocity of the tracer is not only given by the velocity of the surrounding fluid as a motion, as a deterministic motion which pushes the thing around, but there's also these microscopic collisions with other molecules or something like this, which produces additional pushes, random pushes, which are given by the increments, by the changes of position of all these other guys that hit the given tracer. And this is modeled by saying, okay, the tracer alone gets an additional speed component, an additional velocity component, which is given by the velocity of a Brownian motion. So Brownian motion is a certain random motion, and it is equivalently described in a way by saying what is the corresponding velocity of the Brownian motion. And if we want to say that the particle has an additional component which acts on it like a Brownian motion, then we should add to the velocity of the new particle, of the tracer, we should add not only the velocity that comes from the deterministic velocity field around, but we should also add this random velocity which describes the additional random motion by collisions. And then, in order to have a little bit more flexibility regarding the model, we could also think of a certain function or matrix sigma of x, which is space dependent, which is some sort of a viscosity description of the fluid, which tells us how much of this random push by these surrounding molecules is actually really translated to the motion of the tracer. So if sigma as a prefactor, okay, and this if you like, this is some sort of a susceptibility of the tracer for the received pushes by the surrounding molecules, and this susceptibility or this sensitivity of the tracer might depend on the position where the tracer is actually located. It might be at some point in space which is more viscous, where we have a more viscous environment, and where the fluctuations, where the tracer is less sensitive to the fluctuations in those parts of space, the sigma function would be smaller as opposed to other parts in space where the tracer is more sensitive to these pushes. So that would just allow us for a little more degree of flexibility in the formulation and the description of what we want to show. So this would be then something like a differential equation which involves more than just time derivatives. It would involve a derivative of Brownian motion as a random forcing term which acts additionally on this motion. And in the special case, when the velocity or when this velocity of vector field v is 0, and when, say, sigma is just constant, we would think that this is just another description of Brownian motion, namely the speed of the tracer is equal to the speed of Brownian motion, which in other terms would just say that the tracer is just a Brownian motion. But here we have obviously extended the theory of Brownian motion to the situation when we have a Brownian motion under the additional influence of a deterministic drift. So that's what's written here. This model of a dynamics for a particle would be a generalization of Brownian motion to the case of a Brownian motion which is inside a certain velocity field. So it would be a Brownian motion in a swimming pool where the swimming pool has a certain velocity field as in a driving signal. And as a possible trajectory which we observe, if we have an idea how to solve this equation, and if this equation actually does describe what we have in mind as a rough physical picture, then the actual trajectory which we might observe would be this black trajectory, which of course has different properties as opposed to the red trajectory. And of course, in particular in the long run, we would expect that the behavior of the black trajectory would differ quite significantly from the red trajectory. So all this is meant to give a theory, a mathematical theory, which describes dynamical systems under the additional influence of random forces or thermal fluctuations, which is, of course, a very natural thing to ask for when you want to give more realistic descriptions of materials or molecules and so forth. So that what we have written here, this thing which comes with a star, this equation is of course a formal, that's why we put it in quotation marks, and it is an instance of what we describe as a stochastic differential equation. And instead of writing the whole thing with this dot notation for derivatives, we, in stochastic differential equation theory, we prefer to write it with the infinitesimal increments. So we say that the infinitesimal increment of the motion of the particle, of the tracer, is given by the velocity field times the infinitesimal increment of the time, plus the sensitivity matrix or diffusivity matrix, as it is sometimes called, or volatility matrix in finance, times the infinitesimal increment of a Brownian motion. That's how we shall write such an equation in the future. It carries the same amount of information. It's just another way of writing it. And why we write it? Because we will later point out that the derivative of the Brownian motion, which appears here, does not make a lot of sense mathematically. And if you write the dBt, we at least have replaced the older symbol by a new symbol, of which we can still hope to try to make some sense of. Okay, it's just another way of writing the same thing, except for this different style of notation. It doesn't carry any more information. And this is what we then call a stochastic differential equation in standard notation. And if you recall your basic class on ordinary differential equation, for instance, the first step for a rigorous mathematical treatment, typically of ordinary differential equations, in order to come up with rigorous solution theory and so forth, is to understand such an ordinary differential equation, in fact, as an integral equation, or as a family of integral equations. So in order to really develop theory, we will basically introduce a solution concept which does the same transformation, namely we say that a stochastic process X, which is, if you like, the description of the black trajectory, is a solution to this stochastic differential equation, if you like, in standard notation, if and only if for all positive times the process X solves the corresponding integral equation, which is obtained by formally integrating this equation 2 star with regards to the time, to a time interval from 0 to t. And so we end up with an equality which involves the position of the trajectory, xt, and which involves a time integral with respect to the ds, with respect to time, just a straightforward classical time integral over the time interval from 0 to t of this velocity field integrated along the trajectories of the solution. So if you just had this components here, if you just didn't have this stochastic part, then this would be the straightforward and familiar formulation of a solution to an ordinary differential equation as a solution to this family of integral equations. But now we have an additional term which accounts for the random forcing and which involves also an integral from 0 to t. But now, also, if you like, the integral is also taken along this sigma function when evaluated along the solution curve x, but we integrate here with respect not the time increment, but we integrate with respect to the increments of Brownian motion. And in this regard, you see that we have an analogous object which appears here in this theory of stochastic differential equation, which is again an integral with respect to this continuum of increments of Brownian motion. So also here, that's why I said it, also here we have the need, if we want to develop a theory based on this idea, we have the need to give meaning to this integral on the right-hand side. And that's one of the main challenges that's lying ahead of us for the next 1 or 2 sessions, to give a rigorous meaning to this stochastic integral. Okay, let us try to recall what we know when we take a step back and replace this b function, which we in this case interpret just as a random function which is defined on the non-negative time axis and assumes values in the reals. Let us consider and try to recall what we can say when this b function is replaced by a, say, continuous function on the non-negative time axis. And what we were dealing with, for instance, in the finance example, and in essence also in the example of a stochastic differential equations, were basically these weighted increment sums for the function f when evaluated on a finite sequence of grid points, and when we multiply on each of these respective subintervals the increment of the f function with a certain function g. And the question was, for instance, can we pass in such a description or in such a sum, can we pass to a limit when we reduce the mesh size or the step size of the mesh to 0? And in case when the function f, for instance, is the function which plays the role of the increments, or of which we want to evaluate the increments, if the function f happens to be, for instance, differentiable with a, say, bounded derivative function, and if the function g, which plays the role of the theta of the investment portfolio here, for instance, if that's a bounded measurable function, then, in fact, this passage to the limit can be done in a rigorous fashion, and we obtain as a limit a classical integral of the g function against the derivative of the f function when integrated against the time parameter ds here. So that's a simple exercise in one-dimensional analysis to convince yourself that this is the limit. And in this case, we write for the corresponding limit integral, which we had just seen is this classical integral of g times f prime of s ds. We write for this also the integral of g against the infinitesimal increment measure of f, dfs. So if we write, if you like, dfs, we, well, and formally it's the same, because we can replace here the dfs by dfs over ds times ds, which in the first factor on the right-hand side, of course, is another way to write f prime of s ds. So this replacement here of f prime ds by dfs is something that is consistent with our different notations for infinitesimal quantities. And the problem for the application of this idea to our situation of Brownian motion, when we now want to replace the function f, or want to insert this idea, or apply this idea to the case when f is the function obtained by observing one trajectory of a Brownian motion, is that almost surely a Brownian trajectory is nowhere locally Hölter continuous for any gamma bigger than a half. So if you, for instance, choose gamma to be 3/4, so 3/4, then we know that Brownian motion is nowhere locally Hölder continuous with Hölder exponent 3/4. In particular, Brownian motion is nowhere differentiable, because else it would be locally even Lipschitz continuous with Lipschitz constant, so it would be Hölder continuous with Hölder parameter gamma equals 1, but that is in contradiction to our previous finding that the Brownian motion is nowhere locally Hölder continuous, for instance, for Hölder parameter gamma 3/4. So therefore, writing as our stochastic integral dbs, which is the quantity which we wanted to define, so the integral here of gs dbs, writing it is trying to replace the dbs guy by a dbs over ds times ds, and writing the dbs as a b dot ds. This doesn't work because the b dot thing is just infinity everywhere, and it doesn't make sense to do this replacement. So we have no theory which is based on this derivative concept, because simply Brownian motion is not differentiable. The next attempt to derive or to define this integral with respect to the increments of Brownian motion is based on the concept of the Stochastic integral for non-decreasing right continuous functions. This is basically the concept of integration that you know from random variables which assume values in one dimension, because then we have, for a measure in one dimension, Borel measure in one dimension, we always have what we call the distribution function of this measure. And the distribution of this function, the distribution function of a given measure on the real line, is then a right continuous non-decreasing function. So in essence, we have a one-to-one correspondence between right continuous non-decreasing functions on the real line and measures on the corresponding Borel sigma field on the Euclidean line. And if we write this if we want to tell the story by starting from the functions, we have the following definition. So let f be a non-decreasing right continuous function. Then we can introduce a measure starting with very simple sets on which we want to define the measure. Namely, if we have a half-closed finite interval from a to b, then using the function f, we define the corresponding measure of that interval simply as the difference of the function f evaluated on these two boundary points of that interval. That's a function which gives to every finite half-closed interval a certain number, and then we can check easily using Carat-Theodori theorem that this gives a consistent pre-measure on this set on the Borel sigma field, or basically on the field which is on the ring which is generated by these half-open intervals, and this then extends uniquely to a locally finite measure on the Borel sigma field, and this measure mu f, which we have constructed this fashion, is called the Lebesgue-Stieltjes measure associated to the function f. So the short message here is that if you have a right continuous non-decreasing function, then there is a one-to-one correspondence between this function and a certain Borel measure on the Euclidean line, and the correspondence is already completely specified by this equation in the middle. So every measure, Borel measure, is in one-to-one correspondence with a right continuous non-decreasing function on the Euclidean line. Okay, the example that you have to have in mind, as if you like, one of the most extreme examples where this is still applicable, is the case when you consider the Heaviside function. So it's just the indicator function of the positive, of the closed positive half line on the Euclidean line. So here's the graph of the indicator function. That's the right continuous function. And the corresponding Lebesgue-Stieltjes measure for this indicator function, according to this definition, is exactly the Dirac delta measure at the location, at the origin. So this gives you an example of a function f, which is certainly not differentiable, because it's not differentiable in 0, for instance, obviously. But we can still consider the corresponding Lebesgue-Stieltjes measure. And also in this case, we have this approximation result that gives the desired meaning of a corresponding, if you like, integral with respect to the increments. Namely, if we have a continuous function, say, on a unit interval for simplicity, and if we have a function f which is right continuous and non-decreasing, then we can again consider this weighted sum of increments of the function f when the weighting is conducted by multiplying with the values of the g function, of the continuous function, at the corresponding left endpoint, for instance, of the respective intervals on which we evaluate the increments of the function f. And then when we pass in the discretization of the unit interval, which is our time parameter here, if we pass to the limit when the step size goes to 0, which in other words means that the discretization parameter here, n, tends to infinity, then this sum of weighted increments in fact converges to the function of to the integral of the g function on the unit interval when we integrate against the Lebesgue-Stieltjes measure to the function f. And for that, this is then our notation, or our notation for this Lebesgue-Stieltjes integral will be also that we write this as the integral from 0 to 1 of g against the df measure, which is understood as the Lebesgue-Stieltjes measure. Okay, so I want to give a sketch of this result because it's probably not so standard, you haven't seen it before, but on the other hand, the argument is quite simple. Namely, suppose for a moment that we have a function which is in fact just the indicator function of such a half-open interval. Then by the very definition of the Lebesgue-Stieltjes integral, the integral of this indicator function against this measure is of course just the measure of this set. And by definition of the Lebesgue-Stieltjes integral, this is just the evaluation of the function f on the two boundary points, the difference of those two values. Okay, that's just a remark, or just a repetition that we want to have in mind when we now consider the case of this finite sum, namely for discretization parameter level n. We want to consider the function gn of t, which is a linear combination of indicator functions for the respective subintervals which appear in the finite sum, and which are the subintervals on which we want to evaluate the differences of the f function. And this in this linear combination, each of the indicator function of those subintervals is multiplied with the value of the g function, which is the function which should be integrated. Again, it should be integrated with regards to the f function. So these indicator function for an individual interval, let me say it again, is multiplied with the value of the g function on the left boundary point of that interval. Then by the continuity of the g function, we know that for all fixed t, this gn sequence converges to g for all t. It's just a consequence of the g function. So in a way, we discretize the g function with respect to the levels, and we just replace the g function by a piecewise constant function, where on each of these subintervals we replace, or we pick the left boundary point, or the value of g on the left boundary point. And now if we take a look at this weighted increment sum that we want to that we want to investigate here in this lemma, then we can interpret it now as, in fact, the integral of this gn function with respect to the Lebesgue-Stieltjes measure, because the gn function is a linear combination of indicator functions, so therefore the integral of this linear combination is the linear combination of the integrals, and each of these individual integrals are exactly these summands which enter the sum. So therefore this finite sum can be written as, in fact, as an integral, as a full integral involving the Lebesgue-Stieltjes measure of f, with where the integrand, where the function to be integrated is this step piecewise constant function. And now we are in a situation where we can apply just dominated convergence, because mu f is just some measure here, a finite measure, and gn is a sequence of functions which converges for all t to a certain limit function g of t. And if we have an integrable upper bound, which in this case would be, for instance, just the g function, because we assume it's continuous, so therefore it's bounded on this compact interval. So therefore we can apply, in fact, just dominated convergence in order to convince ourselves that this sequence of integrals converges to the integral with respect where the limit function g is what is to be integrated. So this proves the claim that if we have a reasonable Lebesgue-Stieltjes integral for the f function, which is the case, for instance, when the function f is right continuous and non-decreasing, then also in this case we have a proper notion of a integral with respect to the increments of f, and this approximation result also holds true. Okay, that sounds like good news, because differentiability is no longer needed for this construction of the f function, but also the bad news here will show up quickly, because of course the Brownian motion trajectories are not monotone. They are continuous, so in particular right continuous, but in general they are not monotone. So how can we deal with the monotonicity condition, or can we remove the monotonicity condition? And here the idea is to work with the class of functions which are of locally bounded variation. This will be the maximal class of functions where we can still apply this idea of a Lebesgue-Stieltjes integral. And the definition here of a function which is of locally bounded variation is as follows. So, namely, a function which, for instance, is defined on the non-negative time axis is said to be of locally bounded variation if for all non-negative times t, the variation of the function f on the interval from 0 to t is finite, where the variation of this function, that's the quantity s here on this interval from 0 to t, is defined as follows. It is taken as the supremum with respect to all possible partitions of the interval from 0 to t of the quantity which is obtained when we sum up all the absolute value of the differences of the function f. Okay, so the total variation of a function f on an interval from 0 to t is the supremum of all grid variations, of all finite grid variations of the function f. And these grid variations, when delta is a certain grid or a certain partition of the interval from 0 to t, is the sum of all the absolute values of the differences that the function attains when we evaluate the function on the boundary points of the on the grid points which are in this grid delta. So let me say it again. Suppose you have a certain grid which we denote by delta, and by a grid here I want to understand a collection of time points, a countable collection of time points which are ordered, starting, if you like, from time point 0 with index 0 and time 0. And if I fix a certain maximal time capital T, what I do is I evaluate the steps that the function does on each of the pairs of two neighboring grid points, ti plus 1 and ti, but I wedge this, so I take the minimum of these time points with the maximal time parameter t, which I want to consider, which effectively means that I do ignore all possible increments of the function f after time point t. So after time point t, all those differences do not contribute anymore, because I stop effectively the f function at time capital T. So I'm asking for the maximal sum of differences that the function can make in absolute value on these grid points, or on this time interval in total, because for the ultimate value, for the total variation of t, I take the supremum with respect to all possible partitions. Now, if this supremum for all possible partitions is finite for all possible non-negative times t, then I say that this function f is of finite local bounded variation, or just say it's a bounded variation. And the actual main theorem in this Lebesgue-Stieltjes approach is now the following, namely we can have a one-to-one correspondence between right continuous functions which are of bounded variation and the collection of all signed Lebesgue-Stieltjes measures. And this proper statement goes like follows. So a function which, for instance, goes from the non-negative reals into the reals, such a function is right continuous and of locally bounded variation if and only if we find a locally finite signed measure, so a measure which can give back values, not only non-negative values, but can also assign negative values to certain sets. So if we have a locally finite signed measure, such that the following relation between the measure and the function holds, namely a measure of a half-open compact or bounded interval, half-open bounded interval, is given as before, just as the difference of the function when evaluated at the two boundary points of this interval. So in other words, we have a one-to-one correspondence between functions of finite variation, provided they are also right continuous, with the collection of locally finite signed Borel measures on the real line. Okay, let me sketch this correspondence. Namely, assume for a moment that we do have a signed measure on the Borel sigma field on the Euclidean line, which is locally finite, which means that on bounded sets it assigns a finite value. And then I want to evaluate, or I want to, and suppose I define a function with a certain given initial value, which I define an arbitrary function at 0. And I want to consider, and I want to define a function, I want to assume that we have this relation between this measure mu and the function f, which either is something that I can formulate a priori, or I can just define a function f like that. And then I want to prove that this function is right continuous and it is of finite variation. Okay, the right continuity of this function follows directly from the continuity of measure when we approximate sets from above. So therefore, right continuity is a direct consequence. And as for the boundedness of the variation of this function f, we write down for a given grid the corresponding grid variation of the function. Now, by the relation between the function f and the measure, the corresponding increments that the function does on the boundary points of the relative intervals, is therefore just described by the corresponding measure of this signed measure on the on the corresponding parts of the interval. Now, by an abstract theorem in measure theory, which is called the Radon decomposition, I can decompose any signed measure in a unique fashion into its positive and negative part. So I can decompose the measure of each of those subintervals into the positive, the measure of such interval will be the difference of the positive part of this finite measure and the negative part of this measure, which here I want to write in the convention that also the negative part of the measure is a positive measure, but whenever I evaluate on a given measure, I need to take the minus sign for the negative part in front. Okay, so then by triangle inequality for absolute value, of course, these individual summands is bounded from above by the corresponding sum of the two components. And then by additivity of these two measures, each of these individual sums is just the measure of the positive part of the mu f measure and the negative part of the mu f measure of the total interval from 0 to t, and this by local finiteness assumptions is finite. So this tells me that for all possible partitions delta, this increment of the function, or the total variation of the function f when evaluated on this grid, is bounded from above by a finite number which does not depend on the grid, and so therefore this function f is of bounded variation. Again, the right continuity of the function is a straight consequence of the continuity of measure by approximation from above, or if you want to relate it to monotone convergence, just by monotone convergence. So this shows that whenever you have a bounded signed measure, a locally bounded signed measure on the negative real line, then there is a right continuous function of bounded variation which is unique up to an additive constant and which is related to the measure by this formula here. And this measure, then the measure f, is then the Lebesgue-Stieltjes measure. In other way around, we want to assume, if we want to assume that f is a right continuous function which is of bounded variation, and that is assumed without loss of generality that the function is normalized by a shift, that it is 0 at the origin, then if we consider this function of total variation on the interval from 0 to t, it's a little not so complicated exercise to convince yourself that this is a function which is right continuous and of course non-decreasing. So therefore st is a candidate for the classical Lebesgue-Stieltjes integral for the case of an increasing function. And we can also show that if we consider this function st, which we had just discussed, so the total variation of the f function, and here's a misprint. So if we consider so we had just discussed that the function that assigns to each level t, the corresponding total variation of the function f on the interval from 0 to t, that this is a right continuous non-decreasing function, so therefore it's a candidate for a Lebesgue-Stieltjes integral. And similarly, if we consider the function which takes this st, the total variation, and subtracts the function f, which is also right continuous, then this is again a right continuous function as a difference of two right continuous functions. And by a little argument that I leave as an exercise, you can also show that this is in fact a non-decreasing function too. So therefore, we have the Lebesgue-Stieltjes measure for this function g. And of course, we will now define as the mu f measure, the corresponding Lebesgue-Stieltjes measure, to be the difference of the two Lebesgue-Stieltjes measures which both were positive. So this mu f here, this definition, defines a signed measure as the difference of the two Lebesgue-Stieltjes measures which we obtained from the S function and the G function, which were both individually non-decreasing right continuous functions. And this defines a signed measure of a local, which is locally bounded, and which by definition satisfies this relation. And also, as a side remark, this definition already determines or also gives a representation of this Radon decomposition of the measure mu f in terms of its positive and negative part. The previous result had the message that if we have a function that is not necessarily non-decreasing, but which has bounded variation and which is right continuous, then this function still allows for the construction of a Lebesgue-Stieltjes integral, which then will be a Lebesgue-Stieltjes measure, which then will be a signed measure. But still it is possible to integrate another function with respect to the infinitesimal increments of that function of bounded variation. And this is, for instance, demonstrated by the following result, which is just an analog of what we had before, namely if we have a function g which is continuous, which we want to integrate with respect to the infinitesimal jumps of a given function f, and if that function f is right continuous and of bounded variation, then as before we have that this discretized integrals, or this Riemann sum type integrals, which integrate the function g against the increments of f, then this sequence of approximations in fact do converge to the integral of the function g with regards to the Lebesgue-Stieltjes measure that is associated to this function f, when the grid size of this approximation, or the step size of this approximation tends to 0, and with the grid size or step size of the grid we want to understand the maximal difference between two of those grid points in the grid delta. The proof of this result is just the same as the proof that we did for the Lebesgue-Stieltjes measure when the function f is increasing. Okay, so this sounds like good news, but the trouble is that even now the theory does not apply to the case of a Brownian trajectory, because almost no Brownian trajectory is of locally bounded variation, and we will show this with the next two arguments, which will be the conclusion of today's lecture. The first step in order to see this will be the introduction of an important concept which will ultimately lead to the solution of the problem and will ultimately lead to the construction of the stochastic integral, which will be the concept of a quadratic variation of a function. Namely, we say that a function which is, for instance, defined on non-negative real line is of locally bounded quadratic variation if for all non-negative times t, the corresponding quadratic variation on the interval from 0 to t of that function exists, and this quadratic variation is defined as the sum of the squares of the increment that the function does on a certain grid. When we evaluate these sums of squares up to the time point t, and when we send the mesh size, so the maximal step size in this interval, in this collection of grids, to 0. If this limit exists, limit with respect to a sequence of grids whose mesh size converges to 0, if this limit exists, and this limit is independent of the actual collection of grids which we were putting into this limiting procedure, then we say that the function f is of finite quadratic variation, where the term quadratic obviously refers to the square operation that we do inside when we square the increment. So we say that this function is of finite quadratic variation if this limit exists and is independent of the actual choice of a sequence of grids, provided that the mesh size of this sequence of grids converges to 0. Another notation for this quadratic variation is this double bracket, because this is a quadratic operation, so it's some sort of a square operation after all, and the bracket notation will be used later on exclusively. Okay, and we will later argue that the Brownian trajectories are in fact of finite quadratic variation and not of finite variation, and this in particular implies that the variation, the local variation of Brownian trajectories will be infinite almost surely. In order to see this, we have the following lemma, namely let f be a continuous function which is of bounded variation. Then the corresponding quadratic variation must be necessarily 0. Hence, in particular, if we do have a function which has a positive quadratic variation, then it cannot be of finite variation. And if we can show that the Brownian trajectories are of finite quadratic variation, then the variation must be infinite. Okay, let us show this lemma, that if we have finite quadratic variation, if we have finite variation, then the quadratic variation must be necessarily 0. Okay, assume we have a certain grid delta, and we approximate the quadratic variation through this sum of squares that we observe on the function f when we evaluate it on the pairs of endpoints of the subsequent intervals. Now in this sum I can of course take out the supremum of the absolute value in fact of the function f that is in this increment squared, right? So I have a sum of increments squared, and I can, of course, in each of these products, I can estimate one of the two factors by just the maximal increment that I will observe in all these sequence of increments. This is the factor which I take out of this integral as a factor in front in order to obtain an estimate from above. And what remains inside, or after I took out this one factor, it remains the sum of these individual increments, which of course is the term which appears in the approximation of the variation of the function f. And this supremum, okay, so this approximation of the variation of the function f, by definition of the variation of the function f as a supremum of all these expressions with respect to the possible choices of grids delta, this term here, the Farreid's factor, is obviously dominated from above by the variation. And the estimate which I end up with is that this approximation of the quadratic variation therefore is bounded from above by the maximal increment of the function f on two of those grid points multiplied by the variation of the function, which on the right hand side here is a finite quantity. But this maximal increment of the function f of any of those pairs of grid points converges to 0 if the mesh size of the grid converges to 0, because the function f is assumed to be continuous. And therefore, if I evaluate these increments or these differences, I observe a quantity which is uniformly small, provided the two different points of evaluation are close enough due to the uniform continuity of the continuous function f on the compact interval from 0 to t. So therefore I see that if I send the mesh size delta to 0, my approximation of the quadratic variation produces a 0 sequence, and hence the lemma is shown. And the final result of today's lecture will now be that when we deal, in fact, for the first time now with stochastic trajectories, with the stochastic functions, so now we make a step from a fixed deterministic function f to a function which is obtained by observing a random trajectory. Namely, if x is a random trajectory obtained from Brownian motion, or the collection of random trajectories of Brownian motion, then for a given sequence of partitions, I can evaluate the corresponding approximations of the quadratic variation of this Brownian motion at time t, following this grid delta. And I'm saying that this approximation, or approximative quadratic variation of Brownian motion for given time t converges to the constant t, to the deterministic quantity t, when the mesh size converges to 0. And this convergence here in this proposition, which will be strongly amplified and improved in the next lecture, in this proposition it's a convergence in probability, and later we will, as I just said, will provide a much stronger statement than this. But in particular, if we combine this with the argument that I just presented before about the relation of variation and quadratic variation, in particular implies that the variation of a Brownian trajectory is infinite is infinite for all t almost surely, because else we would not have a strictly positive quadratic variation. It would need to be quadratic variation 0 in order to have a finite variation. Okay, let's show this lemma, or this proposition about the convergence and probability of these approximate quadratic variations when we evaluate this along Brownian trajectories. Okay, I consider this quantity, which is this sequence of squares, of increment squares, and I divide or I subtract the number t, which is the suspected limit of this sequence of t delta, and I insert. Okay, I take subtract the suspected limit, and I take the square of this, and finally I take the expectation. So in other words, here I'm heading for a convergence in L2 of this random quantity towards the deterministic number t. So in fact, I'm going to show something stronger than the convergence in L2, and in probability I will show convergence in L2 of this quantity. Okay, here I have a random quantity which depends on the realization of the Brownian path, and here I have a deterministic quantity, and I'm saying that this random quantity, when the mesh size of delta converges to 0, converges to this deterministic quantity. Okay, I write out what this approximative quadratic variation it means. It's the sum of these increments squared, and the t, that's capital of this terminal value t, I write as the sum of the differences in a telescopic sum, and I insert this into the sum. So I'm having this expected value of the sum squared. If I introduce a random variable, which is just the square of this increment, then I see that I'm having here the sum of the zi variables. It's just a renaming or relabeling of the quantities which appear before, if I introduce this random variable, minus the expected value of the zi, where I sum over the zi's. And I take the square of this. Well, this is then nothing but the variance of the zi, of the sum of the zi's, when I is when y is the index over which I take the sum. And since the zi's, they all are dealing with the increments of the Brownian motion on different time intervals, on mutually disjoint time intervals, and therefore by the condition of independent increments for Brownian motion, all these zi's are independent. So therefore, by the Bienname inequality or Bienname equality about the variance of independent sums, this is just the sum of the variances. Now, what is zi? Zi is the square of a random variable which is distributed according to a standard normal distribution with expectation 0. With expectation 0 and variance ti plus 1 minus ti. And therefore I can compute the variance of each of these zi, which in this case is ti plus 1 minus ti squared times 2. So that's a not so complicated computation. Basically, it's the question, what is the variance right there? So it's a simple consequence of the scaling of the psi. And in particular, I can, in this sum, I can take out, as before, the maximal difference that appears in the sequence of ti, which is the definition of the mesh size of this partition delta. And what remains then is this increment of the ti numbers, which, of course, is just capital T by a telescopic sum. So in total, I obtain that the L2 difference, the difference in L2 between this quantity T delta T and the deterministic number T, this L2 difference is bounded from above by twice the mesh size of the grid times the parameter T, which of course tends to 0 when the mesh size tends to 0. And therefore I have proved that this T delta quantity converges to the deterministic number T in L2 if the mesh size tends to 0, which in particular implies also a convergence in probability by the Chebyshev inequality. So in essence, it tells me that the quadratic variation of a Brownian motion is finite, and it is even the identity function with regards to the time parameter. So from this, I'm very close to the conclusion that the quadratic variation of a Brownian motion is just the t function, and in particular implies that the variation of a Brownian trajectory must be infinite, because else I would have 0 quadratic variation. And as a negative result, this tells me that the Lebesgue-Stieltjes integral approach, which is maximally, if you like, applicable to the case when I'm dealing with functions of bounded variation, that this is not sufficient for the case that for the case of a Brownian random function, because we have just seen that Brownian random functions are not of finite variation. But as a positive result, this tells that Brownian trajectories have a finite quadratic variation, and this is in fact the key observation which will then help us to construct the stochastic integral. But this will require a little bit of a detour through some concepts of abstract functional analysis, and this will be the contents of the next one or two lectures.